Today we study speed of light. The Y22, 23, and 24 are for the Einstein's special theory of relativity. First of all, we recall that the Maxwell's equation described the classical electromagnetic waves that consisting of electric field and magnetic field. And in vacuum, they propagate along a direction, and the electric field and magnetic fields are perpendicular to that propagation, direction of propagation. And especially, the speed of the wave, the light wave, is always fixed in vacuum. That is completely determined by this factor, permeability constant and permittivity. Those factors that determines the strength of the electric field. E0 determines the electric field that appears in the denominator of the Coulomb's force, and mu 0 determines the strength of the magnetic field that appears in the Ampere's law. Accidentally, Maxwell noticed that the product of these two numbers that were known by the time he was living, he found, although the number 299,792,458 meter per second that is known as of today, he noticed that the product of the two numbers and take the square root, and the reciprocal of that number is exactly the same as the speed of light. So nowadays we know that all of the electromagnetic wave consisting of well-known visible lights and various wavelengths or frequencies, they are all satisfying the Maxwell's equation. That means the electromagnetic waves are all propagating in vacuum with the speed of light. That is an absolute number that doesn't change at all. Finally, people decided that we need to fix the number instead of increase the accuracy of a measurement. So it is exactly 299,792,458 meter per second. We learned that the electromagnetic fields are satisfying the wave equation. That wave equation is called Maxwell's equations. We first learned the integral forms of the Gauss law for the electric field and magnetic field. And by applying the divergence theorem, we were able to derive the differential form of the electric field of divergence. The divergence of the electric field is proportional to the charge density per electric permittivity of vacuum. The magnetic field is generated by current, and the source of the magnetic field is always consisting of the two poles. That means there is no way to separate the north pole and south pole of a magnet. That leads to a conclusion that they over a closed surface integral, the magnetic field flux always vanishes. That is equivalent to the differential form divergence V equals always 0. In addition, there are two different kind of equations that are dependent on the time. The changing magnetic field generates the electric field. That is called Faraday's law. And current generates the magnetic field around the wire, the carrying current. In addition, just like the Faraday's law, changing electric field generates also another kind of magnetic field. So the first term on the right side says it is Ampere's law, and second term, time-dependent contribution that is related to displacement current is called the Maxwell's law, and the sum of these is called the Maxwell-Ampere's law. If you look at the vacuum, the charge and current completely disappear. Then the equation of motion for the electromagnetic field becomes quite compact and becomes symmetric, except that there is some sign difference. This rho J disappears in the case of vacuum propagation. Let us simplify the equation for the electromagnetic field, only considering the vacuum. Perhaps we need to compute this kind of form, this curl of curl. And we can make use of the back cap rule to find the cross product, double cross product. A vector cross B vector cross C vector. That is called, that can be simplified in terms of back cap rule. And we make use of this back cap rule to find the curl of any vector field. We'll find how this equation can be solved. This expression can be simplified on the right hand side and from the question. Back cap rule, we can apply the back cap rule to find the right hand side, and we find that there is a divergence of V and Laplacian operator applied to a vector field. We recall that this is a gradient operator for x component, x derivative, and then y component and z component. And if it is a square, we have double derivative with respect to x, and double derivative with respect to y, and double derivative with respect to z. That is Laplacian. We recall that if it is a vacuum, divergence of electric field and divergence of magnetic field, both of them vanish. Therefore, this simple relation can be applied if we substitute V equals electric field or magnetic field. We apply the backup rule to find that it is a minus Laplacian of electric field, and curl B is the minus Laplacian of the magnetic field field. We return to the equation, this Faraday's law, changing magnetic field generates an electric field, and that induced electric field is around the direction of change of magnetic field. So the Faraday's law states that curl of E is a time derivative of magnetic field, And for simplicity, we multiply c on the numerator and denominator simultaneously. The reason is that in SI unit system, electric field, magnitude of the electric field and magnitude of magnetic fields are different. We have to multiply speed of light to have an equality. Next, Maxwell's law. This is Maxwell's law. Maxwell's law, we multiply c, speed of light, to the magnetic field. We have vacuum, current vanishes, and then we have c, mu 0, epsilon 0, and time derivative of the electric field. We recall that this is mu 0, epsilon 0 is 1 over c squared. Hence, the result is electric field derivative with respect to not time, but c. Speed of light is multiplied. We can find the dimension of this is inverse of length, and speed of light multiplied by time, differential time. It also has the dimensions of length, 1 over length. So using these results, Faraday's law and Maxwell's law are written in the form. We just have made use of this relation. Why don't we make an operation of curl to both equations? Because once we apply this curl, the left-hand side is simplified in such a way, and if I multiply this curl operator to the right-hand side, what we find in the left-hand side of the original equation from the other equation. Again, the curl of E can be found on the left-hand side of this original left equation. That's the reason why we apply curl operation. So, first we apply curl operation for the Faraday's law. This is written in the form of Laplacian of the electric field. And if we apply the curl operator to Maxwell's law, what we obtain is Laplacian of speed of light multiplied by the magnetic field. And what happens to the right hand side? We keep the time derivative as it is and put forward the gradient operator inside. Then becomes curl of B multiplied by speed of light. On the right hand side of the Maxwell's equation, we obtain curl of E that will be differentiated with respect to speed of light multiplied by time. Now we substitute this result in here. What happens is and then minus then means we have 1 over minus 1 over c squared double time derivative of cb is obtained. In a similar manner, right hand side, curl b is replaced with this one, and this first order time derivative is inserted here to find the similar structure. So we have both left and right side and negative sign. Therefore, what we obtain for the electric field and magnetic field are the same equation. And we recall for any case that satisfies this equation is called wave. And such a wave is a kind of form f x minus vt, something like that. We learned that previously in the first semester. In here, we have electric field that is composed of three components, x, y, and z component. Magnetic field, three components. Every component satisfies the wave equation. And this v is the speed of the wave. Hence, 1 over c squared, that is mu 0 epsilon 0. Therefore, c is the speed of light. So Maxwell's equation says the electric field, every component of the electric field and every component of magnetic field is propagating with the speed of light. The electromagnetic wave is very special in the sense that it does not require any medium, unlike every mechanical waves that require actual medium. For example, sound wave does not travel in the vacuum. However, the electromagnetic wave can propagate in the medium without any medium. However, it was not really convincing at the time that Michelson did measure the speed of light in very accurate way by making use of his device, whose that is called the Michelson interferometer. His interferometer is the most accurate device to measure the length at the scale of level of the wavelength of visible light. With this device, he wanted to measure the speed of light in a very accurate way so that he could determine the relative motion of the Earth in comparison with the absolute frame in which the medium of electromagnetic wave, he believed, is at rest. That medium is called ether. And actually, his measurement wanted to measure the speed of light traveling along different paths that making a right angle. This is the source, and the source generates the electromagnetic wave that is a visible light, and it returns. This is after bouncing back against the mirror, and there's a transverse direction motion, and the two waves interfere in the telescope, and you can find the interference pattern between the two propagating waves. And we are not so much interested in the detail of this device itself, and we simplify this situation. The reason why he divided into this single light wave into two pieces is that the device is fixed on the surface of the Earth, and he assumed that the Earth is moving relative to the rest frame of ether, that is absolute frame in which the speed of light is defined. However, at the end of the day, his measurement did not notice any change in the time difference of the two paths as long as the distance of the horizontal arm and vertical arm, transverse arm, are the same. And he won the Nobel Prize. He's the only person who won the Nobel Prize due to a failed experiment. Actually, the measurement itself was successful. This, the reason why I say this failed is his assumption was failed. His assumption that there is an absolute frame of reference for the electromagnetic wave. The relativity was already studied well before the Einstein's relativity, because the Newton's law of motion, that is F equals ma, is invariant under Galilean transformation. First of all, if you want to describe a system, physical system, you need to choose a frame of reference. Frame of reference gives a spatial coordinates and the time coordinate. Suppose that there is a reference frame S in which time and spatial coordinates are defined as t and x. We can describe the same system in a different reference frame that is called S prime. Here we require the both systems to be the inertial reference frame. Inertial reference frame provides space-time coordinates just like any other reference frame. However, the spatial feature of this inertial reference frame is that the Newton's law of motion is invariant. The F equals ma is always written in the form. Say the law of physics should be the same in any inertial reference frame. An example of a non-inertial reference frame is a frame fixed to a falling body that is making an acceleration. In such a system, we cannot write F equals ma in this way because, for example, the falling body actually receives some force that is F equals mg. However, in the frame where you're fixed to this falling body, then you do not notice that force and acceleration is 0. So we have to choose the inertial reference frame to describe a physical system in an easy way. In general, we can still make use of non-inertial reference frame, but we need to interpret the translation from inertial reference frame to A non-inertial reference frame has some different structure. For example, that F equals ma does not work at all in non-inertial reference frame. It should be modified. The law should be modified. So that's the reason why we stick to the inertial reference frame. The transformation of the space-time coordinates between any two inertial reference frames is called Galilean transformation. Galilean transformation does not change the time parameter at all. It is always invariant. The absolute value may be different because of the translational amount. That may be a constant, but we can always choose it to be 0 by synchronizing the two coordinates. When they meet together, we just set t equals t and t prime to be the same. Then that's fine. The spatial coordinates can be described in the two different reference frame. In case if the relative motion of the two frames is u, then if time flows by t, then the displacement between the two origins, we assume that two origins overlap at t equals t prime equals 0, then the displacement from O prime to O is ut. Suppose that a particle in a frame of reference S is v at time t. If it is moving with a velocity, constant velocity, it is vt. Then the displacement from the origin of S prime should be, following this vector addition formula, we can find that it's just u plus v times t. Hence, the velocity of the same object described in the system of S prime should be u plus v, while the velocity of that particle described in S should be v. That can be found by taking the time derivative of this formula. X prime vector equals x vector plus u vector t, and u is constant, and time derivative. That is because the time is the same in both frames. And we call it, this is a v. This is v. So because v prime, we need to add u, that is the relative velocity between the two frames. If you take another time derivative, you will find acceleration. Here, this one becomes x prime double dot, that is acceleration in the frame S prime. And right hand side, you will get v dot, that is a in that frame. Because the relative velocity between the two any inertial reference frame is constant, it vanishes after the time derivative. Hence, the acceleration in frame S prime and the acceleration in frame S are the same. An additional assumption is the mass of a single particle is the same in both frames. Then we can multiply the identical mass, m prime, a prime is ma. This should be the force in the frame S prime, and this should be the force in the frame S. So the force in the two systems, in the inertial reference frames, are the same. That means under Galilean transformation, Newton's law of motion is invariant. So we apply this Galilean transformation to consider the motion, propagation of electromagnetic wave. Let us simplify. This figure shows this Michelson-Morley experiment. O, E, A, the 3 points are fixed in on Earth. Fixed. And Earth is moving at a short time period. We assume that the Earth is moving with a constant velocity for a very short time in comparison with the speed of light is very small. And we observe outside, assume that there's a either is absolute frame in which the speed of light c is fixed. C is the same everywhere in the frame where ether is at rest. And this is Michelson's original assumption. So if we measure the speed of light in the frame where ether is at rest, we do not have to consider this complicated object because it is by definition, almost by definition, it is always the same. The speed, longitudinal direction, and the transverse direction. They, if the length of each arm is the same, it would take the same time elapsed to return the light from O to return to O. This transverse light returns to this. So we say to the right, to the left, upward and downward. So it would take for up and down, time up and time down, and time to the right and to the left. This should be the same if we measure the speed of light in the frame where ether is at rest. However, because Earth is moving, the speed may be different. For simplicity, we assume that the relative velocity of the Earth is along the horizontal direction. Sure, because we do not know where the ether's rest frame is, so we can rotate the direction in various ways and repeat the same experiment. What really Michelson Morley have a, have carried out is that they have changed all of the directions. Finally, they didn't find any difference between the two paths. So we do not have to consider all possible directions. Instead, we simplify our analysis to consider the case such that the relative velocity of the Earth to the ether rest frame is along the horizontal direction. And we define this fourth left time, and we will sum these two, and compare the time difference. Okay, because we have assumed that the speed of light is constant in any direction in the frame where either is at rest, it is convenient to transform this system, make a Galilean transformation from the Earth rest frame to the ether rest frame. The Earth rest frame, the horizontal light wave travels in this direction, and Earth is moving with the velocity v. Light wave goes in this velocity. When it returns, it should be much faster. In here, the speed is the same. But if in the frame where the frame is moving along the direction, this amount, capital V, should be subtracted to find the final velocity. Okay. In summary, I have shown this. There's two frames, S star and SE. SE is the frame where we are on the Earth, and S star is the either rest frame. And the either rest frame is moving back and forth with the same. For example, we have chosen the unit basis vector E1 hat. It is a C E1 hat and minus C E1 hat in the either rest frame. Because the Earth is moving to the right, it catches up in the Earth. It should be C minus V, the one direction, and when it returns, it is a C plus V, the one hat. So on Earth, when it returns, is faster than the speed of light in the either rest frame. When it approaches mirror A, it is slowed down by the relative velocity of the Earth relative to the ether. That's the reason why we have V to the right in the Earth rest frame is this, and V to the left when it returns, we have a faster velocity. The direction is opposite. If we consider the transverse direction, Earth it is transverse, but because Earth is moving in the frame where either is at rest, it is flying in this way. The either rest frame speed of light is always a c, and this is, if we consider the velocity only, speed of light is this in the either rest frame, Earth velocity is this, then what we obtain in the transverse direction is velocity measured in the Earth rest frame. So this is a capital V. So this is a right triangle. We we would obtain c squared minus v squared is the speed of light in the Earth rest frame when we measure the wave traveling along the transverse direction. So in here, this is a horizontal direction and this is vertical direction when we measure the speed of light in the frame of either rest frame. When it returns, horizontal direction has the same magnitude and direction, and vertical direction, it flips the sign, and this magnitude is same. All right. Okay, there are two typos. If you make a Galilean transformation from the either rest frame to the Earth rest frame, this one cancels. The Earth motion cancels. So this part is wrong, and it should be, we should copy this result. Let's go to c squared minus v squared e2 hat, and when it returns it is minus the square root c squared minus v squared e2 hat is the velocity measured in the Earth rest frame. Okay, the following figure shows the longitudinal motion of the electromagnetic wave in the same experiment seen in the frame of ether rest frame. In the ether as rest frame, the mirror on the side A is moving with a velocity capital V, and original distance between the O and A, the starting point and the place where mirror is placed, is fixed to be L. Because everything is moving that is fixed on the Earth with the velocity capital V, this cube represents the mirror and starting point. They are translating with the velocity capital V. Because speed of light is bigger than the speed of the Earth that is assumed, the red line, that is the track of the longitudinal light wave that is moving parallel, and it catches up with the distance L. So CT to the right and VT to the right, they are the same if we add the distance L. In this way, we could calculate the time required for the light traveling to the longitudinal direction to arrive at the mirror at some time, that is t to the right. And this one can also be computed by making use of the velocity c minus v that we just have computed over here, c minus v and c plus v in the Earth rest frame. So this can be done in this way, and when it returns, because the light bounced back from the mirror, is traveling opposite to the direction of motion of the Earth, so it takes less time because the velocity is c plus v. So as a result, we can compute the time for the forward and backward direction, that is L over c divided by 1 minus beta, and L over c times 1 plus beta. Here beta is v over c. So if we add these two, then we can compute the total time of travel for the longitudinal light. Here we have another mistake. It is a positive sign. We need to add these two times, and sum of these will be the beta cancels, and it is a 2 over 1 minus beta squared. The overall factor is L over C. The factor of 2 is the return round trip motion, and we define the factor 1 minus beta squared is gamma, then gamma squared equals 1 over beta squared. So we end up with the round trip time necessary for the returning to the original point for the longitudinal motion. We can compute the transverse motion. Here we can make use of the velocity. So up and down along the E to head direction measured in the on the surface of the Earth, or we can make use of speed of light in the frame of either raster frame. In either way, we arrive at the same result. So going up and down, they are symmetric. So whether we use this is measured in the either raster frame, and we could use the Earth raster frame result. For example, if we use the either raster frame result, we have a right triangle, this, and we can factor the c squared minus v squared t up squared equals L squared, and L is actually t up equals L over square root c squared minus v squared. Because of the symmetry, t up should be the same as t down, so the total time, that is a sum of the t up and t down, should be 2L over this. And if we factor c out, then we have factor. This factor is called the Lorentz factor. If we compare the previous result, T parallel equals to 2L over C gamma squared, and here T per 2L over C gamma. So gamma is because we assume V is less than C, so this is greater than 1. That means this gamma squared must be greater than gamma. If you subtract t parallel subtracted by t perpendicular is 12 over c gamma, gamma minus 1. Because both this is greater than 1 and this is greater than 0. So this is a positive definite. So longitudinal direction, when it returns, it comes very fast, but when it goes further to reach the mirror at point A, it slows down. So this is the reason why it takes a longer time than when we travel along the transverse direction. So Michelson Morley experiment wanted to measure this gap between the two travels, the longitudinal and transverse, because they did not know what velocity, what relative velocity may have the Earth is moving relative to the either rest frame. They change the direction arbitrarily, and in any direction they have never observed the time delay of the longitudinal direction. So as a result, their experiment has a conclusion. Their assumption that there is an absolute frame in which either the assumed medium of electromagnetic wave but actually there is no such kind of frame at all. That's, then that is the reason why the speed of light is the same even on Earth, the same in any direction. We know the Earth is moving around the sun, Earth, and it is spinning. So every time it changes velocity. However, the speed of light measured even in a non-inertial reference frame, the speed of light is the same as, now we know the exact number, but that is an exact constant. This is the complete failure of Galilean transformation application to the behavior of light. So light does not follow the Galilean transformation, which is satisfied by the Newtonian mechanics for the massive particle. This is the reason for why we need Einstein's relativity. Let us summarize before we go ahead with the relativity. From Maxwell's equations, we have found the electromagnetic wave is propagating with the speed of light, and in the theory, there is no preference of a reference frame. That means the Maxwell's equation should be the same in any inertial reference frame. And that means the speed of light is always the same in any inertial reference frame. Let us see. The Maxwell's equations are combined to find that every component of the electric field and every component of the magnetic field, they are traveling with the speed of light. The problem is that if we apply the Galilean transformation to this wave equation, we do not find exactly the same form at all. That means the Maxwell's equation is not invariant under Galilean transformation. But just like what we have found for the Newtonian mechanics, F equals ma is preserved under the Galilean transformation. We have found that the Galilean transformation is not a correct transformation, space-time transformation rule governing the electromagnetic wave. The big difference between the usual massive particle we observe on the Earth, they are relatively slowly moving in comparison with the speed of light. Because the electromagnetic wave is always traveling with the speed of light, which is very, very fast, we find that the Galilean transformation is making a failure for such a fastly moving particle. Perhaps there should be a exact space-time transformation rule, not the same as Galilean transformation in the limit where the speed of an object is very fast. Instead, when we find a massive particle, or has because of the massive particle, any massive particle has its own rest frame. If one can find the transformation rule that satisfies the invariance of the Maxwell's equation, and in the limit when a massive particle is moving slowly, then that will be the best solution. We are looking for the transformation rule that satisfies the invariance of the Maxwell's equation, and in the limit where velocity becomes tiny, it reproduces the Galilean transformation. That is called the Lorentz transformation. Postulates of relativity. Until now, Michelson-Morley experiment tells us the speed of light is the same everywhere in any inertial reference frame. And the value is now determines to be, because it is a natural constant, we do not extend the numerical accuracy further, and we let it exact. So this is 299, 792, 458 meter per second. Just like the invariance of the Newtonian mechanics on the Galilean transformation, we look for a spacetime coordinate transformation rule that satisfies the invariance of the Maxwell's equation. More generally, this coordinate transformation must preserve the shape of the equation of motion that is stated as it is. The laws of physics are equivalent to any observers in any inertial reference frame. So if you write Maxwell's equation in some reference frame, and if you boost the frame to somewhere else, then you will also find the same equation. That's the invariance of physics laws in any inertial reference frame. And the second one is experimental fact that the speed of light, c, in vacuum is always the same in any inertial reference frame. We are looking for a transformation rule that satisfies these conditions. To describe or to solve this problem, it is convenient to introduce a space-time event. Until now, we use two variables. One has this real one-dimensional number representing time. Three components are combined to construct a Euclidean, three-dimensional Euclidean vector. Why not? We multiply the speed of light that is constant. We rescale the time to make a dimension of length and put them together to construct the whole coordinate because it is convenient to find each component is the same dimension, has the same dimension. We call this one space-time event. An event in an inertial reference frame is determined as the time and spatial components, and time has been rescaled. Next one, the speed of light is always the same. We first compute the velocity. Velocity is defined by the displacement divided by the time difference. So instantaneous velocity is the time derivative of displacement of a massive particle. If we apply this, a particle moving with constant velocity has this form. The full velocity is a ct, and x, that x should be vt. This is the space-time event for a massive particle. What happens to a photon? Photon is a kind of electromagnetic field, the quantum of the electromagnetic field, and it is always traveling with the speed of light. Hence, the velocity v of usual massive particle is to be replaced with the speed of light when we consider the space-time event of a photon. Then, the space-time of photon is written in the form when it travels along the x-axis. All right. Let us extend this idea to the case of a particle that does not move at all. We introduced a time scale that shows it is called tau. C multiplied by tau comma 0 is the space-time event for a particle at rest. Because the coordinates are all 0, it describes a particle fixed at the origin of an inertial reference frame. We want to distinguish this time for a particle describing a particle that is moving, and time to describe a particle that is fixed. It is rather strange in the viewpoint of Galilean transformation, but however, Galilean transformation was proved to be completely wrong for a photon. So why not introducing a different time scale for the particle at rest and particle moving? So we use, by the way, if tau and t are the same, then we shall find that we can prove the Galilean transformation is also true for a particle just like photon that is moving very fast with the speed of light. However, at the end of the just like a reduction to absurdity, we can assume some absurd assumption, and then At the end of the day, if you're logical, you will find that the stupid assumption will be proved to be wrong. And if it is wrong, then you find the other one will be the real answer. So there is nothing wrong. We distinguish the time for a particle at rest and time for a particle moving. So tau is called the proper time, and it is used only for the particle move fixed at a point in an inertial reference frame. And except for that, as long as a particle is moving, we just use parameter t instead of tau. Now we have reached the final stage to verify the time dilation, to verify the fact that time dilation resolved the problem of the final result of Michelson and Morley. In fact, the light wave traveling, one is traveling along the horizontal direction, and the other is traveling along the transverse direction. Both of them arrive at the same time. That means it takes the same time. Let me call it tau. We do not have to distinguish t up and down, t to the right, and t to the left. In the rest frame of the Earth, where the apparatus is installed, still the light travels with the speed of light. The distance, the horizontal distance is L, and transverse direction is also L. Light travels with the speed of light, the equal distance. So it travels to return to the same position. It takes L over C to go forward to arrive at the mirror. The same time is required to arrive at the mirror B. They are all the same. And let me call it tau. Then, because of the symmetry, that there is no difference between the time spent to go forward and backward, and upward and downward. All four times are the same in the frame where the photon's motion is measured in the rest frame of the Earth. So, the length of each arm has the distance, the length L, and that can be measured with the proper time. Although it is traveling with the speed of light, let's see. If something is not moving, time is measured in such a way, c tau, comma 0. Something is moving with a finite velocity that is whose the magnitude is less than the speed of light. For simplicity, we take the constant velocity, then it is not tau, but t. And we assume that tau is not equal to t because the assumption is based on the Galilean transformation, and we have reached the point the Galilean transformation does not work at all for the description of light motion. Okay, so If something is moving with the speed of light wave, it is still t and t. So the reason why I have written tau is although it takes t instead of tau, when it returns to the starting point, there is no motion at all. So the light travels forward to reach A, and the light comes back to the original starting point. Because of the symmetry, the two time, these time t, these two time must be the same. It takes 2t. However, this 2t, after this round trip travel, the displacement of this light after the final stage is the same as the initial stage. That's the reason why I would say it is a 2 tau, because of this. Therefore, I can say the time required for the light to travel to reach the arm A and B are all tau. Now, this figure is identical to the previous figure. Instead, the big difference is that we do not assume the Galilean transformation. In there, tau is always the same as the t. For any inertial reference frame, time is an absolute value according to the Galilean transformation. This is Galilean transformation. We throw this away and we use tau and t. That may be different, and that should be different in order to make this difference between the two times, the horizontal motion time period and longitudinal and transverse difference should vanish because of experimental result. So this is the same form. If we consider the transverse travel returns to the same point. This is Earth. This red line is seen from other raster frame where the Earth is moving with the velocity v. Even though we have thrown away the absolute frame in which either is at rest, we can still choose a frame that has a relative velocity with respect to the Earth. So, in that case, the distance of travel is L and L. And in the frame where the Earth is moving with the relative velocity v, although on Earth is moving along this vertical direction only, it also has the transverse direction. The actual distance of travel in that frame of reference, the light travels along this way. In the two frame of reference, SE, and we previously used S star. In S star, Earth is moving with the velocity v. Okay. Then on Earth, we used proper time tau to consider the motion of the photon because it returns to the same starting point. So the change was c tau times 2 comma 0 vector for the return travel. However, If you look at the motion of the photon in the frame of reference as a star, it follows the red line. Therefore, the net motion is going forward. So there is a shift, there is a displacement. So we would use different time c instead of tau multiplied by 2, and because the actual displacement is vt, factor of 2 is due to the fact that these two are congruent triangles. Finally, if we consider a single part, single direction, this is the displacement of the origin of the Earth rest frame. This is the motion, displacement of photon, light. And this is related to the proper time laser. I told you this vertical direction is related to the proper time because when it returns to the same point, we have to use proper time because there is no motion at all. Now we have a proper time here. Here the two sides depends on the time t measured in the frame, time tau measured in the Earth rest frame, time t measured in the S star frame, in which both the Earth and the experimental device moves forward along this direction with the relative velocity capital V. Now we end up with this identity. This identity gives, we have tau here and t here. We can square these two equations to find and move this one to the right side. But finally, we divide both sides with the over factor. We end up with the final answer. Time is a product of a proper time tau and a factor. This factor is called Lorentz factor, and that is always greater than 1. When beta, that is a v over speed of light, when beta is 0, tau and t are identical to each other. If it is not the case, gamma is always greater than 1. The Lorentz factor's graph depends on the explicit value for beta, and when beta reaches 1, it grows up to infinity. This means that beta will never reach 1, so it approaches 1 minus. That means, what is 1? Beta is v over c. V can never reach the speed of light. This is called a relativistic right triangle. We have reached this point. Time appears in two sides, including hypotenuse. This tau is invariant under any Lorentz transformation. So if V increases, this right triangle changes the shape in this kind of form. If this v decreases, it becomes this kind of form. This is a highly relativistic. Ultra relativistic. And when v goes to 0, this is a non-relativistic. Limit, as can be seen in here. All right, so we have found the time varies depending on the frame of reference. If the watch clock is fixed at a single point, fixed time, a fixed clock shows tau. Moving clock shows t when it's moving with the velocity v, and t is always greater than tau, and this explicit value is a gamma tau, and that gamma goes to infinity as the speed of light, the velocity approaches the speed of light. Thank you.